Cool, thank you, Scott. I want to begin today by acknowledging that I'm speaking to you all from Bellingham, Washington, the ancestral land of Lummi Nation and the Nooksack tribe, and I'll be focusing on work that I completed on the ancestral land of the Puyallup and Nisqually tribes. Next slide, please. So I want to focus on volcanic mass wasting events and their sediment. These are large landslides in volcanic terrain that careen down the slopes mixed with ice and snow and form a slurry that deposits a ton of sediment into the valleys and river systems below. And Avery just gave a great description of debris flows. Those are one type of volcanic mass wasting event. Next slide. So a lot of research has been completed studying the initiation and flow dynamic of these large landslides, but not as much work has been done studying the actual sediment deposit characteristics and what occurs once the sediment gets into the river and begins to move downstream. Next slide. And this is really important because, for example, if the rock material is really coarse and large, then it might move down the river as bedload, eventually depositing and aggregating, resulting in less space for water in the river, which could result in flooding to downstream communities. On the other hand, if the landslide material is really fine, it could move through the system as suspended load or wash load and have little to no impact. Next slide. One thing that can control this is sediment abrasion. This is the idea that big rocks collide against each other as they move along the riverbed and break down to smaller rocks. So if that landslide material is big and really strong, you can imagine those rocks knocking against each other and not really breaking down too much and leading to that flooding. But if those coarse rocks are really weak, you can imagine them bumping against each other and breaking down really rapidly to fine material and moving through the system as wash load. Next slide. So I've been doing some research to answer the question, what is the variability in sediment size and strength of the volcanic mass wasting deposit in the Pacific Northwest? I've been looking at 5 different volcanic mass wasting deposits at 4 different volcanoes. Next slide. And we've been studying this with the hypothesis that the abrasion potential varies substantially between sites with important implications for the downstream impact of those events. Next slide. So today, I want to focus on just 2 of the volcanic mass wasting deposits, both at Mount Rainier. Kautz Creek in red is on the southwest side of Mount Rainier near Longmire and the Nisqually entrance, and Little Tahoma is on the northeast side of Mount Rainier near Sunrise and the White River Valley. Next slide. So I want to give you a sense real quick of what these 2 events were. So in early October of 1947, there was a period of 2 days with intense rainfall, roughly 5.8 inches of rain in that time, and this resulted in 4 discrete glacial outburst floods, which was a flood of water that mixed with sediment to create a slurry with the consistency of wet concrete. This material moved down the valley and ultimately deposited into that fan shape that we see on the left-hand side, making its way into the Nisqually River. And you can see Longmire and the Nisqually entrance pointed out for reference. Next slide. For Little Tahoma, in December of 1963, a large amount of rock broke off of Little Tahoma Peak, careened down the slope and mixed with snow and ice to form a rock avalanche that ultimately deposited a ton of sediment onto the lower third of Emmons Glacier and even more material into the White River Valley below. And you can see that sediment in light tan on the right-hand side. Next slide. So I just want to give you a picture of what this material actually looked like on the ground. Kautz Creek on the left, you can see my field assistants laying on the giant boulders. They're really tired. Those rocks are really durable, and you can see them just sitting there. And then you can also see more fine material up above. On the right-hand side, we have Little Tahoma, and you can see that the rocks are weathering and crumbling in place. And we have that yellow field book for scale. Next slide. So in order to study the questions I posed to you, we had to collect a lot of data. For each deposit we went to, we visited about 10 different exposures. And for each exposure, we set up a grid system with 100 sections. In each section, we chose one grain and measured its grain size using a tape measure, assigned it a lithology type. And for those that were large enough, we used a Schmidt rock hammer, which you can see me holding on the bottom right, to measure the strength. But today we're going to focus on just the lithology and rock strength. Next slide. So when I say lithology, I want to be clear that I'm not talking about petrologic lithologies. We assigned them categories that we felt were important to river transport and abrasion. So was it plutonic or granitic? Was it volcanic? Did it have bubble holes or not? And was it hydrothermally altered? What jumped out to me is that if we look at the pie chart, Kautz Creek on the top is dominated by the non-vesicular volcanic rock in dark purple. It does also have some granitic rock, but if we look at Little Tahoma below, this is much more mixed. It has a lot of the light purple vesicular rock, and it also has the hydrothermally altered rock in orange. Next slide. So here I want to take the lithology type and think about what they mean in terms of strength. So we have strength broken up by lithology and for each deposit. On top, we have the light pink and dark purple, which are associated with stronger rock type. And on the bottom, we see that the light purple and orange are associated with weaker rock type. Next slide. So if we take those lithologies and the strength and put them all together for each deposit, what we end up with is that Kautz Creek is made up of stronger rock, and Little Tahoma is made up of weaker rock, which means it has a higher abrasion potential if we think about those rocks colliding with each other and breaking down really rapidly to fines. Next slide. So what does this all mean for the landslide material and how it transports downstream? Well, here I used the lithologies for each deposit along with their corresponding strengths and plugged them into a simple downstream transport abrasion model. So on the y-axis, we have the fraction or percent of the landslide material remaining. And on the x-axis, we have the distance downstream from the source. So at 0 kilometers, we have 100% of our deposit. And as that material moves downstream, it begins to abrade and produce fine material, which we see in white. What is immediately clear is that the mass wasting material from Kautz Creek, which is dominated by the stronger non-vesicular rock in dark purple, is not abrading a whole lot. I wanted to note that at 25 kilometers, the Nisqually River does enter Alder Lake, so all this material is likely deposited into this lake. But hypothetically, if the lake were not present, it's likely that this coarse material would largely persist all the way down to the Puget Sound. In contrast, the Little Tahoma mass wasting material, which has a lot of the weaker light purple vesicular rock and orange hydrothermally altered rock, is abrading to find far more, with 71% volume loss by the time it reaches 100 kilometers downstream near Tacoma. Next slide. So in conclusion, we looked at one volcano, Mount Rainier, which has the same glaciation and volcanic eruptive history, but we looked at two different deposits on opposite sides of the volcano. Next slide. And these volcanic deposits have different volcanic rock sources with different rock properties. Kautz Creek was more durable and stronger, whereas the Little Tahoma material was crumbling and weathering and breaking down more rapidly. Next slide. And this has important impact for our river system. The Kautz Creek material, which is stronger, would abrade far less. And hypothetically, if that lake weren't there, it would continue to move downstream and potentially cause flooding to the areas along the river. Now, I do say hypothetically, but this idea can be applied to other mass wasting events in the Pacific Northwest and to other sediment pulses worldwide. The stronger material will abrade less and persist further downstream, potentially causing flooding, whereas weaker material would abrade rapidly and wash through the system as fine. Next, please. So I want to say thank you to all you amazing people that helped me collect this data, and I'm happy to take any questions.
All righty. Are there any questions for Brian? Hey, got a question from Taylor. In Kautz Creek, how do you differentiate between rocks produced by the mass wasting event and those already in the existing floodplain material or glacial moraines, or did you?
Yeah, so Scott, if you could go forward a few slides, I have some more pictures of Kautz Creek. Unless you didn't see more. There we go. So there have been a lot of mass wasting events in the Kautz Creek area. There's pretty much one every single year. So that was definitely something that we had to kind of wrap our heads around and deal with. That Beeson showed us had some work done previously that showed us a type deposit of what this material should look like. So we went out there and found that and used that sort of as a reference for what we wanted to look for. But the other kind of important thing to consider is that most of this rock is being sourced from a very similar area. So even if we weren't 100% accurate on which deposit we were necessarily looking at, it should have been really similar material. But on the whole, we had a mixture of the really fine sediment with the kind of larger durable rock, and we were able to kind of pluck out a 2-meter section along the exposure that we felt pretty confident in were the deposit we were looking for.